So today we're going to talk about the gamma distribution, beta distribution, and bivariate normal. Alright, so the gamma is related to the exponential and the Poisson distribution in that if you have n variables that are exponentially distributed, then the sum of those will be gamma. Okay, so if all the xi's are exponential, then the variable tn, which is the sum of all these exponentials, by definition has the distribution of gamma. Now the mental picture, let me draw it here in the bottom, and in the context of the Poisson process, okay, which is what I'm interested in here. Right, so we have time 0. Okay, and then if we have all these xi's, right, so that's the time between arrivals or between events. So for example, if the first event happens here, like the first earthquake, so that means this is x1, right? The second earthquake will happen here at this time. All right, now that's going to be x2 and so forth. It's supposed to be something's wrong with my pen today. Okay, I can't erase. Alright, so that's supposed to be x2 and then so on and so forth. Alright. So we keep going, and that's, let's say this is the last arrival. Now this time right here is going to be tn. Oh, that's supposed to be 10, right? So it's the arrival time of the nth event in the Poisson process. Okay, so that's what I want you guys to remember about the gamma distribution. Is the time right here of the nth event, and that's the nth event. All right. Okay. So that's the notation gamma. This is the PDF. Now we're not going to go into detail about how to derive it. And so as you see, it's a complicated formula. So the way we're going to work with it is use calculators, or online calculators such as this one, or your own calculator. Okay. So yeah, we're going to do an example about that. These are the expected values and variances. Alpha divided by beta, alpha divided by beta squared. Now, let's talk about the parameters, because that causes a lot of confusion. So in the context of the Poisson process, the parameters are n and lambda. So n is the number of events, so the arrival time of the third bus, for example, n is 3, and lambda is the usual parameter for the Poisson process or exponential, right? It's the rate, the average rate, the average flow. Okay, but in general, you can use this distribution for other random variables because it's so malleable, let's say. We're going to see shapes of this in a minute. So in the general context, the parameters are alpha and beta. Now, typically alpha equals n in general, right? So parameter alpha is always, in the context of the Poisson process, again, it's the arrival number that you're interested in, and then beta, for the most part, is going to be lambda, but not always. And it depends on your calculator. Not always, right? So that's why I have this remark right here. So, like the online calculator that we have here uses beta equals lambda, but there's some other ones online that would use beta equals 1 over lambda. Okay, so you need to be careful about that when talking about the gamma distribution. All right, so that's pretty much all I wanted to say about the gamma. Now let's look at the online calculator here. Oops. Okay, so let me put it in focus here. All right. Yeah, it's a little small. Let me make it bigger. Yeah, so this is your typical online calculator, right? On this particular website, you can choose if beta is going to be the rate or the scale parameter. Okay, so let's use it as a rate, so it's just equal to lambda, right? Oh yeah, and they put it equal to lambda in this case. All right, so let's do the first example right here. So it refers to example 174, which we discussed in class last time, I think. All right, but anyway, so in that example, we had, let's show it real quick. So we have earthquakes. These are the time in days of the time between big earthquakes in the world. And you see how our exponential distribution fits very nicely. Okay, so here the average is 437 days. That's all we need to know. Okay, so in that example, so the time between earthquakes, so let's call it, let's call it X. For some reason I can't erase today. Anyway, okay, so xi is going to be the time between earthquake I and I plus 1, I guess. Right, so it's the time between earthquakes. And this is the guy that is exponentially distributed with rate lambda, and lambda is 1 over 437 days, right? Because they gave you the average time between earthquakes, which is 437 days. So lambda, which is the rate, the flow, it's the inverse. Okay, so part A is what is the probability to have 2 earthquakes the next year. This one typically you would do with Poisson, and that's fine. So you can do it with the Poisson distribution, right? And why? Because all these distributions are related, Poisson exponential and gamma. Right, so we know that the number of earthquakes in 2 years is Poisson with parameter lambda times 2 years, right? So we could do it like a Poisson, but here we're doing it with the gamma because it says using gamma, right? So here t is the variable of interest, so t sub 2 in our notation, right? Tn, so n is the, but n is 2 here, this second earthquake, right? So so this is the time the second earthquake occurs. All right, and this guy is gamma distributed with the first parameter is 2, right, and then the second parameter is lambda. So the question here is probability T2, that should be a 2, less than 1 year, right? Now, since lambda is in days, well, it's in 1 over days, so let's do it in days, so 365. Okay, and that's it. And then we're going to use our calculator. Let me use the online calculator right here. So alpha is 2, lambda is 1 divided by 437. Yeah, so here we're not done yet. So for x, we said it's 365 days, and we want the probability that it's less than that, right? Hey, what happened here? 1 divided by 437. What? Okay, so yeah, let's use the other one then. Right, because it's not working. So this would be 1 over lambda, so 437. Yeah, there we go. Yeah, so I guess this online calculator cannot do that operation, 1 over that. Okay, so that's your distribution, right? Looks nice and skewed. Here's 365, and we want the probability that it be less than. And there you have it. All right, so it's 0.203. Okay, and this is the general shape of these distributions. So it's not bell shape, it's like a skewed bell shape, right? It is only for the positive numbers. And you can see here if we change it to 6, for example, so the 6th earthquake, you see that the mean goes way to the right. And by the way, in the bottom row, you see you have the mean variances and all that. All right, so that's the gamma distribution. Oh wait, let's do part B here. What is probably the third earthquake happens after 10 years from now? So same thing, right? Here is T10 is the time of the 10th earthquake. Sorry, third. T3, right? All right, so let's just start here. So third earthquake, that means alpha is 3, same parameter, beta. And here we said 10 years, and then in this case, 10 years is going to be 365 with a 0 there. Okay, and then, wait, probably the third earthquake happens after 10 years. All right, so after would be 1 minus that. Right. Oh wait, what happened with the 10 years? Okay. So it's, I don't know if you can see it, but it's right around the 4,000 mark. So it's so little, so it's 0.01. Okay, so that's how we work with the gamma distribution. Typically with a calculator, because doing it by hand is not really an option. Okay, let's look at the beta distribution. We're going to talk very little about it because it's also hard to work with it by hand. We just do it online. And we're not going to use it actually, but you need to know it because it in practice is very useful. The reason it's very useful is because apart from the uniform distribution, it's the only one that has a sample space that it's an interval. So typically it's the whole real line or the whole positive numbers, but on an interval there's only the uniform, right? That is defined between two numbers a and b. But and the uniform is, the shape of it is not very flexible, right? It just looks like a rectangle. So that's why the beta distribution is so useful in these cases, because you can get almost any shape. Oops. All right, and let's focus on the graph. So here you have the PDF of the beta up here, right? And depending on the two parameters, alpha and beta, you see all the shapes you can get, right? So from the green that looks like exponential, it could go up. So I mean, almost any shape you can describe with these two parameters. That's the main benefit of the beta distribution. You can shape it to almost any histogram, right? And it only has two parameters, and it's only confined on a finite interval. In this case, between 0 and 1. But those you can change between any numbers a and b. All right. So that's the beta distribution. Really, all I want you guys to know is that it's so flexible and that it's the only one, apart from the uniform, that works on a finite interval, okay? Very good. All right, now finally, the bivariate normal distribution, probably one of the most important ones. And again, it's hard to work with it by hand, unless few special cases. So again, we're going to work with the computer to evaluate all the integrals and all. All right. So that's the definition. That's the PDF of the bivariate normal. So the bivariate normal is one where x1 and x2 are normally distributed on their own, but they have a correlation. Okay, so that's the PDF in vector form. All right. So if you compare it to the original PDF of one variable, it's very similar. Before, in the original PDF, this would be sigma. Okay. This is the inverse of the covariance matrix. Right? So it's like plays the role of 1 over sigma in the other one. And finally, these two, x minus mu transpose times x minus mu, plays the role of x minus mu squared in the scalar case. All right. Then we have the vector mu of the means of x1 and x2, and these are covariance matrix as usual. Now recall, these are the variance on the diagonal, and this term is the covariance x1, x2. Okay, and that is the same as the covariance between 2 and 1. And by definition of covariance, this is also an alternative, right? That the covariance equals the correlation coefficient times the standard deviations of sigma 1 and sigma 2. Okay? Now, let me show you how it looks. So in the top here, that's a distribution where both means are at 0, and then the standard deviations are, 1 and 2. And the covariance is, the correlation is 0.7. Okay, so this is a 3D plot. Right, it's a mountain. Now, it's skewed like that because there's a correlation of 0.7. If I change it to 0, just to see how two independent variables would look, that's the situation, right? So now the contour lines are all circles, right? And we can see it from the top, which are kind of the figures I have here on the bottom, which shows you the same picture but with different correlation coefficients. So from negative 0.7 all the way to 0, and then the positives 0.7, 0.5, etc. You see it's the same shapes, but just in the other directions. So I plot another case where the correlation is high, let's say 0.97 and negative point. Let's see what happens. All right, you see, so the first row here, column, that's when the correlation is very high, and it looks like it tends to a straight line. All right, so if I put 1, it's probably going to throw me an error, division by 0. But you see the effect of the correlation on these contour plots, right? So the more the correlation, the more things are concentrated along a straight line, which is the meaning of correlation, right? All right. One of the things about the normal distribution, if I do that, right? So I'm looking at just the y plane. That would be the marginal distribution of y, right? And it looks normal. Also, I can do the same for x, right? I just rotate it. And if I look at it in this way, that would be the marginal of x. And you see the shape is normal. Okay? And that's actually one of the main things. So the bivariate normal has these 3 effects, and we're going to go one by one. So the first one is that the marginals are normal. We're not going to prove any of these, we're just going to know how to use them. They're normally distributed with the mean mu I and variance sigma I squared, as usual. Right? And that is what I'm doing here. Now let me just try another correlation so you see it works for any correlation, 0.5 for example. Alright, so if I do the same, if I look at just in the x density plane, like that, that also looks normal. Centered at 0 with a standard deviation of 1, because the variable x has a standard deviation of 1. Now for the other variable, yeah, I do the same. And although there's a correlation, the shape of the mountain changed. The shape of the marginal doesn't. Hope you can see that in what I'm doing. Still we see a normal distribution, which is kind of magic, frankly. Alright, so that's the first property, is that the marginals are normal distributions with the given coefficients. Alright? Okay, and then fact 420 here is that the conditional distributions are also normal. Alright, that's less intuitive. So from here, conditional distributions would be if you were able to cross this or intersect this mountain with a plane, right? It would be the cross section of this mountain would also be normally distributed, is what it's saying. Okay. Now, yeah, I can't do a cross section right now. All right, so what this is saying is, let's see it from this figure. Right, so it's saying that the conditional distributions are normal as well, but with this mean and variance. Okay, so let's draw. So we're going to have x1 here and x2 up here. Okay. Yeah, this, I don't know why I can't do it too now. There you go. All right. So there's going to be a correlation coefficient, right? So we already know, we saw these pictures, right? So everything is slanted along a line with the correlation coefficient. Right, so let's say that line is around here. Okay, and so what this is saying is that that's that line. That's the expected value of x2 given any value x1. So it's saying that, let me try to scroll down a little bit, not so much. Anyway, okay, it's saying that the slope of this line is rho times sigma, times sigma 2 divided by sigma 1, right? That's the slope of this line. Right, because that's the one multiplying x1. All right. Also, it's saying that when x1 equals mu1, so let's say that mu1 is here, the corresponding value of x2 is mu2. So this line actually passes by the mean of x and the mean of x1 and x2. That's supposed to be a 2 again. Okay, so this line crosses the mean value. Now, in the last chapter of this class, we're going to call this the regression line, the linear regression line. Okay, so keep that in mind. All right, so the mean of x2 is given by this line, which depends on x1, right? And then the variance of x2 is independent of x1, right? It doesn't. And it's just 1 minus rho squared times sigma 2 squared. So you can think of it as the distribution of, so given the value of x1 right here, the distribution would have to be normally distributed along, so with this mean, right? So if you imagine a 3D axis, it would be kind of like that. Okay? And normally distributed around the variable x2. And you see this distribution changes for different values of x1 right here. It slides along the regression line, right? So, yeah, and the variance is constant. So you slide this shape along this line and the shape remains the same. Because again, the variance of x2 given x1 doesn't depend on x1. All right, and the third important property is that when you know that x1 and x2 are bivariate normal and their correlation is 0, it means that they're independent. That's the only exception to the rule. I remember that in general, covariance or correlation equals 0 doesn't guarantee independence. That's always true except for the bivariate normal. So if for a bivariate normal you have zero correlation, then it means that they're independent. All right, yeah, these are kind of the same pictures I showed you before. So just to see how the shape of the contours and the mountain, the joint PDF, change with these parameters. All right, take a moment to read this. So pause the video maybe. Okay, so this is real data, by the way, so it's a real distribution. Turns out that the miles per gallon that a car would give you, right, it depends if you drive it on the city or on the highway. So on the city, typically, you get lower mileage because you have to stop and all that. And then the freeway, you get more mileage. All right, so it turns out that these two variables, the mileage on each, it's well approximated by a bivariate normal distribution with these parameters. All right, so these are the mean miles per gallons for city and highway, and this is the covariance matrix, right? So if we know the covariance matrix means that this is the variance of x2, right? And that this would be the covariance x1, x2, which is also equal, and we give it the name sigma 1, 2, remember? And this is just sigma 2 squared. Yeah, for some reason, I can't do the 2's today. Sorry about that. Anyway. Okay, so let's go down these questions. Wait, first let me show you the distribution. Right, so, I mean, you don't have to focus on the coding or anything, just the figures. But just to tell you, this is the data. these numbers, these pairs of numbers. So that's my sample size here. All right. And each data point, so the first one, 1622, is for a given car and, make and model. That's the mileage. The first number is the mileage on the city streets, and the second is the mileage on the freeways. And then we collect all the data, and you can do a histogram as the one below. Okay, and this would be your bivariate distribution. Now, if you look at it like this, you should compare it to one which is maybe this one on top, right? So you see that the correlation is very strong. In this case, it's 0.9, right? Because it's slanted almost along a straight line. All right, and then, yeah, that would be your 3D histogram of this data. All right. So what is the correlation between x1 and x2 in this case? All right. Now, I don't know what this is doing there. All right, and we have a formula for the correlation, right, is the covariance of 1 and 2 divided by standard deviations. And we have all that from the covariance matrix. So the correlation is pretty high, it's 0.9, okay, as we saw in that previous figure. Part B, what's the distribution of the city mileage? So that would be the distribution of a marginal, right? It's only the first one, the variable x1. And by the fact that we just saw, it's normally distributed, with the mean given 18.6 and the variance of 25.2, which again, so the mean is this one and the variance is right there. C, find the average highway mileage for cars with city mileage of 15. Okay, so this is a conditional one, right? And it's actually the same formula we saw before, like this one. Right, for 17a. Okay, so in this figure is the mental picture. So they're asking what is the value of x2 right here at the line. So given x1, what is the value of x2? Okay, and so that's just evaluating this line at the point 15. Okay, and then if you replace all these values, you're going to get 23.2. Make sure you do that. All right, so part D is a little more difficult. It's the same question as part C, but now it says for a city mileage of 15 or less. So it could be any number less than 15. So considering all cars that have a city mileage less than 15, not only those that have exactly 15, as in figure C, part C. Okay, so here is where we need to start integrating these PDFs. So we need to do it in the computer or in a scientific calculator, but by hand we cannot, right? So probably you'll have a homework where you will be able to use numerical methods to solve these integrals. Okay, so the first line here, so, and again, let's compare C and D. So C is equal, given x1 equal little x1, which was 15 in this case. Now here is less than x1, okay? Or less than or equal, but it doesn't make a difference, right? So what we do is we're going to use the total probability rule, right? So let me start here actually. So for total probability, remember, we're going to put ourselves in all possible situations, right? So it's like we're going to take this formula and then integrate it for all values of x1. and then multiply by the probability of x1. In a way, it's like taking the average of this equation taking the expected value of that equation with respect to x1, right? Now in part C, you know the value of x1 is 15, but in part D, we don't know. It's all the values, right? So one way is to put that formula, the same formula up here, right? This is the exact formula we had before. Now S is the dummy variable for integration, right? So it plays the role of x1. But now we're integrating S between negative infinity and x1, right? Because it's 15 miles or less. And then computing the expected value of the point x2, right? Because this is x2 given x1. Yeah, I'm sorry about my pen not working today. Okay, so it's like we're taking the expected value of that function with respect to x1. Now, x1 has to be less than 15 in this case. So the PDF we're going to use for taking expectations is the conditional distribution of x1 given that it's less than 15 in this case. All right, so yeah, here we could, you could put 15 instead of x1. Now in this formula, that's just the formula of the conditional distribution, right? So it's going to be, right, the density of x1 divided by the CDF. Now why is that? It's because the definition of conditional distribution. Remember conditional distribution, so you have probability of A given B, right? So the numerator would be the intersection, right? But the intersection, you see, of these two events, right? One event, let me erase this. All right, so that's event, this is like probability of A and B, right? And with A being that event, so just x1, and that would be event B. Okay, so the intersection of A and B, so A is just really x equals x1, and then the second one is less than x1, or less than or equal, because they're, so you see the intersection is just x1. Okay, the probability of x1 equal to little x1, and that's the density. All right, and then the conditional probability formula says divide that, the intersection of A and B, divided by the probability of B. And the probability of B here is the probability that x1 less than little x1, which is the definition of CDF, right? So it's just a conditional probability formula, but in this special case, okay? All right, so you could do it that way, or it's really the same amount of effort, but so in the second alternative, we recall that expected value is a linear operator, in that it comes in summations, right? So the expected value that we're taking here, right, the integral and everything, x1 is the only random variable, so the expected value only will affect x1. All right, and this equation is the same equation of the line we just drew, but instead of x1, we put this, which is the expected value of x1 given that it's less than 15. All right, recall little x1 is 15 in this analysis. All right, but then to obtain this expected value, you have to do this integral, right, which is the same integral as before. But instead of having the whole equation as the integrand here, you just have S. Okay? All right, so hopefully it makes sense. I know it's a little more involved than your typical example, but it's just to show how useful the bivariate normal is. Because at the end, everything goes back to being normally distributed. But it has this added challenge that we need to compute all these integrals numerically. So you need to learn how to do that. Either MATLAB, Python, whatever you're comfortable with. Mathematica, Wolfram Alpha, all that. All right. Part E, find the percentage of mid-sized cars with at least 19 mpg and CDs at least 26. Right? All right, so there's a straight probability computation. So the area, it's a good idea to always draw it, right? But in this case, it's pretty easy. It's, x1 greater than 19 and x2 greater than 26. So it's just this double integral, right? And this is your bivariate normal distribution, which is the one we define, the first one, this one right here. Okay, now, if you're going to do in the computer, in MATLAB, let's say, all these softwares have already all these PDFs and CDFs defined for you, so you don't have to type in this equation. There's going to be a function, called bivariate normal or something like that in each software package. All right, so that's this double integral. All right, and part F, assuming that 75% of the driving is done in the city, find the expected mileage and the probability. All right, so here is a situation where we say, like in my commute, right? First, I drive like 15 minutes on city streets and 20 minutes on the highway or so. So there's a combination, and I want to know what's my actual mileage, right? So we introduce the random variable y here, which is going to be the mileage of that type of driver. And so here's the model that we postulate, right, is that y is going to be the weighted average of x1 and x2, right, which makes sense. So y is going to be your actual mileage by driving like that, and it's a combination of city and highway. All right, so that's one of the applications of linear combination, right? You take different weights of each random variable. All right, and we've done this many times, right? So we know that since x1 and x2 are normally distributed, then any linear combination is also normally distributed. So y is normally distributed, right? Normally distributed with this mean and this variance. And we already know how to compute these mean and variances, right? This is the covariance of x1 and x2. I'll make sure you know how to get that. All right, and then once we have the mean and variance of y, then we can compute any probability. In this case, they're asking probability less than 25. And this is just a straight normal probability calculation. Very good. All right. Now, that was the case of two random variables, x1 and x2. We can extend this to any number of random variables, in particular n random variables, right? Now, it turns out that the mathematics are all exactly the same, except that you have more random variables. But the same results are true in that these ones, right? That all the marginals would be normal and all the conditionals will be normal. And also, if the correlation between any two is 0, they will be independent. Okay. Now, we're not going to do examples of more than 2 for now, but just keep in mind that all the analysis we did kind of extends nicely to more dimensions.